Welcome to my new calculus channel. My name is John Gabriel. And if you'll recall, in the previous video, I discussed some invalid constructions of real numbers, namely those by Dedekind and Cauchy, and just showed you how those constructions don't actually work. And of course, that was a follow-up on what are decimals and infinitesimal expansions, which don't really exist. But in this video, I'm going to show you a little bit more of how we got those infinitesimal expansions. So let's begin. Now, what I want to look at is this document here. Now, some of you may recognize this, probably most of you won't, but this is Newton's masterwork on infinitesimal calculus. And looking at the first chapter, Per equationes numero terminorum, and my Latin's not that good, so the pronunciation may be very off. But it means the equations for infinite series, okay, or the equations for endless series or of infinity. So at any rate, Newton begins by telling us what he's going to discuss in this particular chapter. So in this first section here, it says, Methodum generalem quam de curvarum quantitate per infinitam terminorum seriem mensuranda olim excogita veram insequitibus breviter explicatam potius cum accurata demonstratam habes. So I think what that basically means is that it's a general method for quantitative curves, which are measured by endless series or infinite series, and briefly explained in the following demonstrations more accurately. Okay, so he begins here and he starts with curvarum simplicium quadratura, and that means quadrature or simple curves. So, and he doesn't really say anything here because he begins by saying, see, if ax to the m over n is equal to y, then it shall be, or erit is then, or shall be, this expression is equal to the area of ABD. And that's obviously false because all he's done there is he's just simply said that this here is the primitive function of this one over here. And you'll see that he actually uses this later on to calculate areas. But it's not, strictly speaking, true that this is the area of ABD, okay? In this particular diagram, and in fact, this may not even look like the curve for ABD. But that doesn't matter so much here because he's looking at it generally. And you'll see these m plus n's and everything. So now you can kind of get an idea why I used that also in my new calculus definition. In the first and only rigorous formulation, well, I had studied Newton's work, and so I just basically got accustomed to seeing him use those particular letters. So at any rate, he gives some examples of derivatives and their primitives. So this is the function, and this is its derivative. And then finally, he gets down to what he intends to do with the infinite series. And this starts right over here. Alarum omnium quadratura, and that means for all other curves. Well, that's also not actually a given But at any rate, he starts with this function here, y is equal to a squared over b plus x. And he uses this method of partial divisors, okay, which he demonstrates in here. And it's from this method from which he decides that it's a good idea to call this equation here the representation of the infinite series and vice versa. Obviously, it's a bad idea, and I'm going to show you now why it is a bad idea after I demonstrate the method to you, okay? So let me demonstrate the method to you quickly. So get my writing pad out here, okay, and right, and I've done this before in previous videos, so I'd advise you to go back and read the videos. I mean, I watched the videos so that you can get an idea of what's happening. So what we have here now is A over B minus C. And that, of course, is just the same as saying A divided by, I didn't actually want to do that, A divided by B minus C. And so naturally, partial divisors, you can choose any one of these. And to understand this better, I suggest you watch my video called Teaching the Method of Long Division, which explains this very simply. But at any rate, the first term that's going to appear up here is A over B. And A over B times B is going to give us A, and A over B times C is going to give us minus AC over B. And subtracting this from this, we'll have AC over B. And again, B goes into this expression plus AC over B squared, right? And so we'll have AC over B minus AC squared over B squared, and that will give us AC squared over B squared. And you can see that generally the terms are going to look something like this, okay? In other words, AC over B squared plus AC squared over B cubed plus ... Now, Newton calls this here the infinite, that's A, by the way, the infinite series representation of this particular expression. And he gets to use this a lot because he does things like AA over B plus X, and he wants to actually integrate this. So he uses this long division method, gets a series, as you see over here, and then he integrates term by term, okay? But now, I just want to show you why this method here is not really a good way of doing things, okay? And so the first example I'd like to give you is this one here. So I want to show you now that if you let A equal to, let's say, 2, B equal to 10, in this expression here, by the way, not this one, this expression here, B equal to 10, and C equal to 2, then you'll have a division sum which looks like this, 10 minus 2, 2 divided by 10 minus 2, okay? So this is the same as saying 2 divided by 10 minus 2, which is the same as saying 2 divided by 8, which is a quarter, right? Okay, so again, we do the same story, and what we'll have here is, let's say 2/10, which is going to give us 2 minus 4 over 10, and subtracting these, we're going to have 4 over 10 like that. And naturally, we can even change the order of the partial divisors, and instead of saying 10 minus 2 now, we can just say 8. And if we do that, what's going to happen is we're going to have plus 5 over 100, like so, and that's going to give us 40 over 100, which is the same as 4 over 10, and there's no remainder left, right? So in this case here, I've shown you that you can actually express a quarter in base 10, because if you remember in the last video, I told you that in order to do that, you need to have the denominator, which is 4, contain the same prime factors as 10. All right, and you can see here that it does contain the prime factors too. So that's why it terminates. Of course, if you have to try this with a is equal to, let's see, a is equal to 3, and b is equal to 10, and c is equal to 1, then what you'll have is 10 minus 1 into 3. And you'll notice that you can start off with 3/10 and continue like this, right? And you'll see that no matter 3/10, by the way, this is 3/10. I didn't really write that well. Let me just fix that. 3/10. Okay. 3. 3/10. And then if we multiply, if we add the next one in, which is 3/100, like so, then you'll see we'll have, again, 3/10 and then minus 3/100, like so, and that will leave us with 3/100. And then, of course, you'll see that there is just no way, whatever you do here, even if you just decide to switch this to a 9 or any other partial divisor that you like, you're never going to be able to finish this expression finitely. In other words, there isn't a last term, as you see often expressed over here, okay? So if you watch here, this is the way, this is the method Newton would use over here to say it carries on forever, okay? Ampersand C. Now, Euler used exactly the same approach here when he decided to produce his ill-formed definition, which I've explained to you in a previous video. I think you may recall that I told you Euler defined S is equal to lim S, okay? That was a pretty bad idea. Now, so Newton, going back to this work of Newton, and I'm a little rusty on it, he tried to show you how you could basically work with all the quadrature of all other curves using this approach. In other words, expanding into infinite series and so on, and then finding the integral that way. And then also a method of root extraction. Okay, so this was when you have binomials with rational, or let's say rational numbers whose denominator is not the unit. In other words, something like a half, a binomial to the power of a half. So anyway, this is quite a long book, and it gets quite a lot more complicated than this, and there are errors. The most important part of this book was what I realized, which is what is found on page 96. Let's just go there. I think it's page 96, if I'm not mistaken. And let's see here. Okay, 96 is all about finite differences. Oh gosh, still further on. 96. All right. So this is methodus differentialis, or differential methods, and this is where Newton got his interpolation polynomial, and eventually Taylor got his Taylor series from this, and it's also where I got my idea for the Gabriel polynomial. And of course, Newton's method, like Taylor's method, was not exact. The Gabriel polynomial has a closed form. And of course, if you rotate this diagram around, it's easier to see that these are actually applications of the mean value theorem on the first difference, but after that, they're all approximations. In the Gabriel polynomial, there are no approximations. Every subsequent order difference, finite difference, is exact, and it can be found using the mean value theorem. Okay, so now I think I strayed a little bit there. I just wanted to give you an idea of partial divisors and how Euler got his idea to produce that famous blunder, S is equal to lim S. Now, another important work that I read when I was still in my teens is the work by Bishop Berkeley. And it's a fascinating work that he produced, asking many incredible questions. For example, if we read this paragraph here, it says, men too often impose on themselves and others as if they conceived and understood things expressed by science, when in truth they have no idea, save only of the very signs themselves. And there are some grounds to apprehend that this may be the present case. And then he talks about Newton's ideas of fluxions and fluents, and quite candidly shows that Newton didn't know what he was really talking about. He was experimenting. He couldn't explain his principles. So here's another beautiful problem here. It says, you may operate and compute and solve problems thereby not only without an actual attention to or actual knowledge, and the principle whereon it depends and whence it is deduced, but even without having ever considered or comprehended them. So this last section is very important. Without having ever considered or comprehended them, all right? And then, of course, he points out some very obvious errors in Newton's work, especially with respect to the differential triangle. And let's see if I can get to it in his refutation. Yeah, so Newton had this idea that ABC is similar to CFH if they are triangles. But that's not what Newton said exactly. In fact, Newton had, if I can draw on this, let me draw on this here quickly. Okay. Screen sketch. Okay, so in reality, and I think I need to pick out a color here. So let's go with red. Now, this triangle is similar to this one, but Newton did something else where he had a curve like that, and he was saying that this region here, or this geometric figure, is similar to that one, but it can't be similar because CFH would have been the one that is similar. So Berkeley discusses these things in quite a bit of detail, and there are some interesting comments that he makes. And let's see if I can find a few more, but you can download all these articles. So here was the original diagram where Newton said that TPB is similar to BRN, but it's not, okay? It's similar to BRL. And of course, what Newton wanted to do here was try to pull the wool over everybody's eyes with the rot of infinitesimals and evanescent quantities and all that bullshit. Obviously, Berkeley wasn't fooled, and a lot of people after Berkeley weren't fooled either. But what's interesting here is that Newton was dealing with something like this, trying to find the areas under curves and also the gradients of the tangent lines, and he didn't realize that this could be solved using the Euclidean proposition, book 5 and proposition 12, which I've already shown you in previous videos, okay? So if you say a general proof of new calculus derivative, you'll see that this particular video here, general proof, actually solves the tangent line problem without any of those ill-formed concepts, okay? So I'm not going to play it now, but you can watch that in your own time. And let's go back to the document. So this paragraph is quite a candid paragraph by Berkeley. It says, I have no controversy about your conclusions. In other words, Berkeley wasn't questioning whether the results from Newton's bogus calculus were correct. He knew they were correct because they were falsifiable, okay? And anything that's falsifiable is really what we're looking for, isn't it? If it's not falsifiable, it's not correct. So, but he says, I have no controversy about your conclusions, but only about your logic and method, how you demonstrate, what objects you are conversant with, and whether you conceive them clearly, right? So it says what principles you proceed upon, how sound they may be, and how you apply them, right? And he says, I'm not concerned about the truth of your theorems, but only about the way of coming at them. So a lot of the refutations and a lot of the objections that he had were very valid. And most of the morons in mainstream academia have never really realized these things. So again, down here, Berkeley says, the truth of the conclusion will not prove either the form or the matter of a syllogism to be true, inasmuch as the elation might have been wrong or the premises false. And a lot of these things happen because of what I've tried to explain to you before, ill-formed ideas. And he says, and the conclusion nevertheless true, though not in virtue of such elation or of such premises. So he says, I say that in every other science, men prove their conclusions by their principles, and not their principles by their conclusions. And of course, he started off with this very first sentence over here, which says, and it should be, and it should seem that whatever errors are admitted in the premises, proportional errors ought to be apprehended in the conclusion. In other words, be they finite or infinitesimal, and that therefore the akrivia of geometry, in other words, the precision or the accuracy of geometry requires nothing should be neglected or rejected, okay? So Berkeley not only pointed out that Newton's methods were not systematic, okay? They were kludgy, and calculus was not made rigorous by the morons that followed, people like Weierstrass and Cauchy and Leibniz. Well, Leibniz came before, but Cauchy and Weierstrass and others that did a lot of work on the calculus, supposedly rigorizing it. There was no rigorous calculus before my calculus was discovered, the new calculus, okay? And it's not really mine because well-formed knowledge is not owned by anyone. However, I will remind you that I was the first in human history to realize this formulation. So I'm proud of that. Okay, at any rate, just let me summarize this whole video. So I wanted to show you that this method here of long division with partial divisors, etc., doesn't actually produce anything concrete in terms of infinite series, because you can call this series here infinite, but it's not infinite because it can't be reified. It has no last term, okay? Infinity cannot be reified in any shape or form. And therefore, it's not a good idea to say that A over B minus C is equal to what you see over here, okay? Not a good idea. It's not true, because there is always a remainder of missing terms. Unless, of course, as I showed you here in the case of a quarter, which can be represented in base 10, the series is finite. And this particular series here, 2 over 10 plus 5 over 100, tells us exactly the measure of 1/4. Very well. So in the next video, we'll continue to discuss these things and learn more about all the fundamental concepts, try to cover some of the fundamental mathematics in Euclid with respect to area, volume, and so forth. So I hope you've enjoyed this presentation and that you will join me again next time. This is New Calculus Channel, and I am the great John Gabriel. Till next time, goodbye.